A very good morning to each and every individual who is seeing this presentation. My name is Shivam Rai. I have completed my master's from Gautam Buddha University, Department of Applied Chemistry, Uttar Pradesh, India. I have done my master's in applied chemistry, and this is the presentation which I gave during the partial fulfillment of the requirements for the award of the degree of Master of Science. Topic of the presentation: research dynamics of the top 1% articles, that is highly cited articles related to electrochemical carbon dioxide reduction and to metric analysis. So now I would start with the presentation. I have to start with something that is somewhat paradoxical, that is fossil fuels. Because this is the incumbent technology, 80% of our world's energy comes from fossil fuels. They are a massive worldwide resource, extremely abundant, have a huge energy density, high power density, and are chemically stable. They are easy to store and transport, cost effective, and highly convenient. Therefore, any future energy technology will need to compete with these attributes. 87% of the energy humankind uses every second, including most of the energy I am using as I speak this presentation or I present this presentation, comes from burning one of the fossil fuels: coal, oil, or natural gas. Electrochemical reduction of carbon dioxide to make fuels and chemicals using renewable CO2 free energy sources and input is to achieve those attributes, and with the right superposition of technologies possible. As identified, carbon dioxide is the most common greenhouse gas in our planet. It is a necessary material for the growth of all the Earth's plants and many industrial processes. Unfortunately, with the intensified industrial activities by mankind, more CO2 is released to the environment, causing Earth carbon imbalance, leading to possible global warming issue. Therefore, reducing CO2 production and converting CO2 into useful materials at the same time seem to be necessary and also critical to the environment protection, can be signaled by the increased investment from various governments worldwide to address the CO2 issue. Among different technologies addressing the CO2 issue, there are two major approaches. First one is to capture and geologically sequestrate carbon dioxide, and the other is to convert CO2 into useful low carbon fuels, as you can see in this figure. However, the conversion of CO2 into other high value added products require a high energy input because of the highly symmetrical structure of CO2 and the highest oxidation state of carbon. So far, CO2 is mainly converted into C1 compounds: methane, methanol, formic acid, etc. Compounds: ethane, acetic acid, ethanol, formate, etc. Cyclic carbonate, dimethyl carbonate, carbonate, decanoate, salicylic acid, and other chemical products for catalytic conversion. Electrochemical conversion, photochemical conversion, enzymatic conversion, plasma conversion, and bioconversion. And in this presentation, I'm going to focus on the electrochemical CO2 reduction. Also, solve the problem of increasing dependency on fossil fuel replacement with renewable energy is the best solution. Electrochemical conversion of CO2, which would potentially be used to reduce greenhouse gas emissions, receive much attention from scientific communities since a carbon neutral energy cycle can be achieved in combination with renewable energy sources. Moreover, the reduction of CO2 is a key element for sustainable development towards the low carbon economy. In our work, the evolution of electrochemical CO2 reduction research from its inception to its status in the past 10 years, that is 2011 to 2020, is analyzed using the bibliometric or scientometric method. VOSviewer was used to visualize the data collected from the Web of Science during the period mentioned. The influence of countries, institutions, authors, and other aspects are analyzed, and the research dynamics in the top 15 countries during research in the field of electrochemical CO2 is introduced for the first time. Also, the historical background regarding electrochemical CO2 reduction is discussed in detail with respect to the timeline of the published articles, and the most impactful researchers are identified. Given the recent heightened research activities and increasingly deepened understanding of the process, we believe that an up to date account on their status and existing challenges is necessary so as to provide researchers with a current snapshot of this rapidly evolving area. To the best of our knowledge, no study has reported a trend in scientific research on this topic disclosed within the wide range of publication years. The objective of our study is to provide quantitative analysis and statistics on the trends of publications over a wider range within the timescale and explore the structure of established networks and trends in the last 10 years. So, the comprehensive analysis of highly cited top 1% articles in terms of development trends, countries, research institute, collaboration networks, citations received, bibliographic coupling, co-authorship, and co-occurrences of terms, which would successfully exhibit the bibliometric portrait of the research in the field of electrochemical CO2 reduction. Now, as you can see this timeline, the effect of carbon dioxide on global warming has been long known with research as early as 1896 by Arrhenius. His paper entitled On the Influence of Carbonic Acid in the Air Upon the Temperature of the Ground, greatly describing the relationship between increased anthropogenic CO2 emissions from burning fossil fuels and increase in retention of the sun's radiation. Current world energy consumption is highly dependent upon fossil fuels. Concerns are growing that the increasing human activities would not only accelerate the consumption of fossil fuels, but also result in escalated greenhouse gas emissions and breaks the carbon balance in the natural world. Since late 19th century, CO2 concentration in the atmosphere has increased from 280 400 ppm parts per million, that is as represented in this figure. During 1970s to 1980s, Japanese scientists pioneered the research in the field of electrochemical CO2 reduction, along with many other sustainable technologies, sparked by Japan's alarming lack of natural resources. Then in 1990, United Nations launched talk aimed at producing the first global climate agreement, leading to the adoption of UNFCCC, that is United Nations Framework Convention on Climate Change, in June 1992, which declared its objective to be the stabilization of greenhouse gas concentration in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. Also, innovation and research funding from industries and governments are often driven by international policies. In the energy sector, some of the policies that have driven research and investment have been Climate Change Act 2008 in the UK, the Energy Independence and Security Act of 2007 in the USA, the more recent Paris Conference of Parties, that's COP21 agreement, which aim is to limit global warming to plus minus 2 degrees Celsius. Effect of these policies is also reflected in our research where developed countries like USA and European countries like Germany, South Korea are having high impact in the field of electrochemical reduction of CO2, as you can see. Japan, Canada, Australia, Switzerland, Singapore, England, Spain, Netherlands, Denmark, India, France, these are the countries which are affecting these fields. China and USA being dominant. Yoshio Hori, the Japanese scientist, and with his colleagues discovered that polycrystalline copper electrodes in aqueous media could generate short chain hydrocarbons with promising activity. Since the pioneering works by Hori et al. In 1980s and 1990s, great efforts have been devoted to the design and engineering of CO2 reduction reactions, electrocatalysts, especially within the past decade. And in all of these research from 2011 to 2020, conducted in labs, which is translated into journal articles, mentions the contribution of Yuichiro Hori's milestone works, which is presented by this map. This map is developed by the VOSviewer visualization method, and this is the cited authors, the most cited authors, in which you can see the bigger the circle, the more cited the author is. Yoshihori is the most cited one. Please note that the distance between the two authors in the map indicates the relatedness of the authors in terms of co-citation links. Closer the two authors are located to each other, the stronger their relatedness. And in this map, which is representing the cited publications through visualization of all the data, that is 2004 articles published. 2004 are the number of articles published, right, between 2011 to 2020, collected from Web of Science. Figures represent the co-citation analysis performed in the VOSviewer, which is a data visualization software. Here, the distance between two publications is indicative of the relatedness of the publication in terms of co-citation links. The closer the two publications are located to each other, the stronger their relatedness. Two publications are co-cited if there is a third publication that cites both publications. The larger the number of publications by which two publications are co-cited, the stronger the co-citation relation between the two publications. As it is evident from this map, three of Hori's papers are among the most cited publications with total 1077 citations. Right? One you can see on the upper part, represented by the red circle, Yoshi Hori 2008, Modern Aspects of Electrochemistry, Springer, that's a book chapter. It's the most cited publication of Yoshihori. Then there is Yoshihori 1989 paper published in Journal of Chemical Society. And then there is Yoshihori paper in 1994 published in Journal Electrochem ACTA. Also, figure. This figure, which you are seeing right now, represents the overlay citation network of all the publications where the color differences of the circles signify the research activity in terms of citations. Color bar at the bottom right corner of the map indicates the citation received by the publications. For example, publications colored in red are having citations more than 500. Again, as I said earlier, that the book chapter titled Electrochemical CO2 Reduction on Metal Electrodes, published in 2008 in Modern Aspects of Electrochemistry by Springer, is the most cited publication of Yoshio Hori, in which he actually introduced the role of copper metal as catalysts and the products, multiple products which it was producing. Now, coming to the methodology section, this flow chart, which you are seeing right now, outlines the step taken to retrieve the relevant papers for this work. Construction of a search string is the most crucial task in bibliometric analysis, and such a step determines the relevance of the publication extracted from Web of Science to the research objective. The search string was designed to retrieve the publication to find an answer of the following questions. First, how has the landscape of carbon dioxide reduction research evolved? Second, research dynamics and advances take place worldwide through screening of top publishing countries, organizations, authors, and journals. To understand, third point, to understand the research dynamics as far as the electrochemical reduction of carbon dioxide is concerned from the perspective of bibliometric analysis so that to be able to find the gaps and future direction in the quest to create an artificial carbon cycle. The raw data were collected on 10th February to 2021. There were 2,418 papers. Some interesting facts evolved during the research indicating that majority of publication, that is 93.1%, 2252 papers, was from 2011 onwards. Only 166 papers were published before 2011, that is 6.87% of the total publications. Based on this observation, timeline from 2011 to 2020 has been selected. Top 15 countries holding major share of the publication were USA, People Republic of China, Germany, South Korea, Japan, Canada, Australia, Switzerland, Singapore, England, Spain, Denmark, Netherlands, India, and France. Full records of all selected publications coming from the top 15 countries, that is 2004, which contained the author's name, title, sources, abstract, keywords, and cited references, were exported in text file format, tab delimited. Finally, the documents retrieved were vetted using Microsoft Excel 2019 to remove the duplicates and merge similar keywords because different authors have individualized differences in the expression of the same noun. Therefore, keywords with different expression of the same meaning need to be combined. That was done in VOSviewer. Also, from this map, it is clear that USA and China are the most productive and impactful countries in the field of electrochemical CO2 research. In this map, the link strength between USA, that total citation more than 30,000, and China, total citation more than 25,000, is 7 lakhs. A link strength is indicative of the number of cited references to publication have in common coming from two countries, in case of bibliographic coupling links, which is represented by this map. Total link strength of US and China are 18 lakh and 23 lakh, which is indicative of the total strength of the links. Connection or relation between two items of a country with other countries. Highly cited articles are very different from ordinary cited articles, and that's the statement which I am saying right now because we have selected top 1% articles, top 1% highly cited articles for our research. So I would repeat, highly cited articles are very different from ordinary cited articles. Typically, they are authored by a large number of scientists, often involving international collaboration. Collaboration and research production are intimately related. Authors with the most papers are generally quite collaborative. Collaboration spreads the workload, which leads to higher collective output. In this overlay visualization map, which you are seeing right now, the top 1% highly cited publications are linked to each other based on bibliographic coupling. Two publications are bibliographically coupled if there is a third publication that is cited by both publications. In other words, bibliographic coupling is about the overlap in the reference lists of the publications. The larger the number of references to publication have in common, the stronger the bibliographic coupling relation between the publications, and they tend to be located close to each other in the visualization. In this map, a color bar is shown at the bottom right corner of the visualization, determined by scores of items, which in this case is indicative of the number of citations received by a particular article. Also, if a paper is highly cited, it is considered to have a more significant influence on a specific topic than do other less cited papers. In this context, highly cited papers have been regarded as potential candidates for identifying and monitoring excellent scientific research and a research group scientific performance. Exploratory study by Tidson et al. Concluded that highly cited research papers do represent useful indicators for identifying world class research. In our study, the top 1% papers with the highest citations were found to be from the top 15 countries, which hold a major portion of the article published in the past decade, including the top 10 authors, as you can see here: Jenske Norskov, Thomas Jaramillo, E.H. Sargent, P. Stresser, Peterson, Andrew Peterson, Philip de Luna, David Sinton, Beatrice C. Roldan, K.P. Kuhul, right? Kendra P. Kuhul, Gopamark team from Netherlands. Also, the top 10 journals. The first one being the Journal of the American Chemical Society with more citations, then ACS Catalysis, and so on. Now, this figure, which you are seeing right now on the map, represents the co-occurrence network of the keywords extracted from the title, abstract, and keyword list given in the articles and provided by the authors. Keywords are assigned to a cluster based on a computer algorithm. Each cluster has its own color. The bigger a circle, the more frequently the keyword appear in the publication set from Web of Science. The lines connecting the circle represent the frequency of the two keywords co-occurrence. In this map, countries are linked to each other based on the number of publications they have ordered jointly, right? Which you are going to see right now in this map, right? So the countries are linked to each other based on the number of publications they have ordered jointly, visualization of which is discussed by Tidson, Person, and Silverster in 1993. The links attribute indicates the number of co-authorship links of a given country with other country. The total link strength attribute indicates the total strength of the co-authorship links of a country with other country, which I have also discussed earlier in earlier maps, right? As represented in this map, USA and China are the two most collaborative countries. On the other hand, France and United Kingdom, the papers, the top 1% paper coming from France and United Kingdom, each with each one paper, were not, they were individual. They were written by individuals and not in collaboration with other other researcher of other country, right? So yeah, now coming to the result section. The electrocatalytic reduction of CO2 has long history, dating from 19th century. In 1870, Royer first reported CO2 reduction to formic acid on zinc electrodes. Right. Uh, Also, I want to say that as you can see in this map, uh, these are the authors, the researchers, which were the most cited ones. The most cited authors, which were the which were basically extracted from this data. This map was basically extracted from the top 1% articles. When we analyzed it uh, on the VOSviewer, the map which showed that Yoshihori was again the most cited author in all those top 1% articles. Then there is Kennepi Cole, Krishna W. Lee, Jenske Norskov, and Andrew Peterson. And these are the same authors, but also the top 10 authors, right? As far as the number of citations concerned. So yeah, this was the thing. Now, as I was talking about the history, so as far as the historical background of the electrochemical CO2 reduction is concerned, it started from the 19th century. In 1870, Royer first reported CO2 reduction to formic acid on zinc electrodes. Then in 1904, Cohen and John used amalgamated zinc, and amalgamated copper with high hydrogen over potential as cathodes to electrocatically reduce CO2 in aqueous sodium bicarbonate. and potassium sulfate solutions, in which formic acid was the only product. In early stages of the research, the main product was found to be formic acid, and the purpose of carbon dioxide conversion was producing organic substances from the cheap carbon resource, that too organic acids, formic acid holding most of the attention, later evolved into the motive of alternate source for fuels. However, to reach the final goal of CO2 electroreduction, challenges and opportunities exist at the same time. For the CO2 reduction reaction itself, optimal catalyst with high catalyzed activity, selectivity, and stability should be developed, which can be used to reduce energy consumption during the CO2 electroreduction process. So far, carbon dioxide is mainly converted into C1 compounds, methane, methanol, formic acid, etc. C2 compound, that is ethane, acetic acid, ethanol formate, and C3 compounds like glycol, hydroxy, acetone, and glyoxy. The reason why it is preferred electrochemically because that allows the energy source that is used to be an CO2 free renewable source such as wind or solar, but in order to do it electrochemically, we need to split the reaction into two half reaction: water oxidation, which occurs at the anode, and carbon dioxide reduction, which occurs at the cathode. Thermodynamically, water oxidation occurs at 1.23 volts and carbon dioxide reduction occurs at 0 volts. Unfortunately, carbon dioxide reduction is a very difficult reaction. So we need to apply an excess voltage to make the reaction go forward, which we refer to as overpotential. The addition of this extra energy makes it less efficient. So one role of catalyst is to decrease the extra voltage that needs to be added to make things more efficient. Other role is selectivity. We can make many different products of carbon dioxide, so we need a catalyst that makes the single product that we are interested in and for our desired application. The other reason is that unfortunately hydrogen evolution also takes place at 0 volts and is a kinetically easy reaction, so it is difficult to find a catalyst that will favor a carbon dioxide reduction over hydrogen evolution, but that's what is needed to be done. We decided to look at transition metals as catalysts for this reaction because there was already a significant amount of literature available to find out by analyzing the bibliometric networks of keyword mapping, bibliographic coupling between publication, and co-citation linked publication. Moreover, some understanding of this reaction on transition metals, and the first step was believed to be that carbon dioxide is reduced to carbon monoxide via two electron to proton reduction. And once you form carbon monoxide, and one number of different outcomes are possible, depending upon the binding energy of the carbon monoxide to the metal surface, usually visible as in this figure, right? Which you are seeing. Now, what is so special about copper? Because Yoshihori also worked on copper. He actually pioneered the work. And right now, copper catalysts are the most efficient ones because they produce multiple products. So now, metals that bind carbon monoxide very strongly, this platinum, nickel, and iron, can end up mainly producing hydrogen gas from carbon dioxide reduction. Because once you form the carbon monoxide, it stays on the metal as a poison and is not released and is bound so tightly that it cannot go on to react further. And so you get hydrogen evolve and breaks in this monal layer of carbon monoxide on the metal surface. On the other hand, metals that bind carbon monoxide very weakly, such as gold, silver, and zinc, tend to produce mainly carbon monoxide because as soon as it's produced, it's released from the metal surface and again cannot go on to react with hydrocarbon and alcohol. The exception to this amongst the transition metals is copper because it has an intermediate carbon monoxide binding energy. So the carbon monoxide is not released, but it is not bound so tightly that it cannot go on to react further and be reduced to hydrocarbons and alcohols as represented in this figure. As you can see, the copper binding strength, it is intermediate, right? It is in between. That's why. As you can see, gold and silver are on the lower side and platinum and palladium are on the higher side. These are the basic concepts basically. Also, the top 1% of publications, right, as you can see in this figure, this in this graph basically, including review and research article pointing toward the development of transition as a catalyst, more specifically copper. Moreover, the increasing citation of these articles over the past 3 years, as presented in this graph, which shows the trend in citation of top 1% papers from 2018 to 2020, indicates that the Paris Climate Agreement 2016 has further accelerated the research process, as most of the citations, on an average more than 70%, has come in the last 3 years, that is 2018, 19, and 20. Therefore, it can be predicted that the research intensity in this field will continue to increase in the coming years. Now, I will conclude my by drawing attention towards the most intriguing part of the research. Climate concerns are reshaping the map of energy. The Paris Agreement of 2015 galvanized the march towards a lower carbon future. It provided new impetus to develop carbon capture, use, and storage, or CCUS, right? Carbon capture, use, and storage. That meant finding commercial applications beyond putting the fizz into carbonated soft drinks. Most recently, on the Earth Day, Elon Musk announced the largest incentive prize in history, which is the carbon removal prize of $100 million, aimed at tackling the biggest threat facing humanity, fighting climate change and rebalancing Earth's carbon cycle. The much discussed energy transition from fossil fuels to renewables may actually facilitate the research direction towards the field of CO2 reduction and utilizations. Energy remains a globally interconnected industry, which is also visible in our analysis of the research regarding electrochemical CO2 reduction, which shows high collaboration network between countries and institutions. Declaring that climate is Europe's most pressing challenge, Ursula von der Leyen, President of the European Commission, has pledged to turn all of Europe into the first carbon neutral continent in the world. What if we reframed CO2 as a feedstock rather than a waste product? That is the question which we started with while encountering electrochemical carbon dioxide reduction, and the same question is asked by the founder of the energy tech company named Opus 12. At Opus 12, the founders have shown to make 16 different carbon based compounds out of carbon dioxide. And this is the same paper, which is also one of the highly cited articles analyzed by us. And it is one of the authors of this article is Kendra Kuhu. As you can see on your left side, on the extreme left, the lady is Kendra Kuhu. She was in the group of Thomas Jaramillo from Stanford University, one of the famous groups working on electrochemical CO2 reduction. Also, recycling CO2 is considered a holy grail of green chemistry, and so many different industries are expressing their interest in this technology and also investing in companies like these. Because earlier, the compound which was considered to be a waste product is now proving to be a new revenue stream. The Opus 12 process uses the electrochemical reduction of carbon dioxide, which uses water and electricity as input. Currently, their focus is on three compounds, namely ethylene, methane, and syngas. Ethylene, the precursor for most of the world plastics, is made from ethane, natural gas, or naphtha oil, and its manufacture releases up to 2 tons of CO2 per ton of ethylene produced. If ethylene were made using their process, it would consume 3 tons of CO2 per ton of ethylene, and you would avoid the 2 tons of process emissions. They are developing this CO2 to ethylene process for NASA. On the other hand, syngas is a critical building block that is used in a wide range of applications, from creating an airtight environment for food preservation to manufacturing performance, homes, and pharmaceuticals at large scale. Syngas can be converted into diesel or jet fuel. This is an alternative way to electrify transportation, create liquid fuel that work in today's infrastructure and engines, but which are produced from renewable power and CO2 rather than from oil. They have received funding from Shell for their approach to renewable syngas. But here, one interesting question arises that why NASA is interested in their technology. Because the CO2 to ethylene process being developed for NASA has potential applications for human spaceflight, as well as producing fuel and chemicals on a potential future moon or Mars base. The Martian atmosphere is comprised of around 95% CO2, which would provide an ample source of CO2. Water ice has been discovered on Mars, and electricity could be provided with solar panels or a nuclear reactor, enabling the electrochemical CO2 process to take place. Many of the CO2 derived products that Opus 12 is commercializing on Earth would play a critical role on a Mars mission. Methane can be used as rocket fuel and as feedstock for microbes to create food or medicine. Ethylene can be used to create 3D printable plastics for tools, containers, and shelters. Producing carbon monoxide from CO2 with our process consumes no net water. Our process means the process developed by Opus 12, right? And thereby offering an attractive way to generate oxygen without consuming the limited water resources of Mars. This may sound like a line coming out straight out of a science fiction book, but we should not forget that the early science fiction is now reality. As renewable electricity becomes even cheaper, the breadth of markets that companies like Opus 12 can address expands. The biggest cost is electricity, so the company can be cost competitive when low cost renewable electricity is available. Preventing CO2 emissions from entering the atmosphere is imperative to deal with the climate crisis, and changing waste emissions to a vital feedstock will provide a further incentive for industries to decarbonize. That was from my side. Thank you so much.